Well, Simon has now given us a fascinating insight into Turing's life after Bletchley Park. And now I'm very pleased that Kevin Murrell, who's a trustee of the National Museum of Computing and also Secretary of the Computer Conservation Society, is going to talk to us in more detail about the Pilot Ace, because Turing may have lost interest in it, but it doesn't mean it wasn't a fascinating computer. Kevin.
Right. This is a fairly vicious device, isn't it? I warn all of you. Pretty dangerous. Thank you. I'd like to talk a bit more about the Pilot Ace machine and then show you a simulation of the machine working. Now, before I can show you the simulation of the machine working, I need to get you all up to speed with programming the Pilot Ace and to explain why the Pilot Ace was different from other machines of the time. To explain how it was different from other machines at the time, I have to explain to you how the rest of the world was programming computers. So, as Bill said, we might be asking questions afterwards. Just to explain some of the components of the machine, this picture that we've seen before actually was one of the publicity shots in 1950 when the machine was demonstrated to the public in November and December. That's the main valve processor rack, and this rack is some, if it's 10 inches deep, that's all it is. So it's quite a thin rack. The control panel is down here, and the control panel has changed over the years, so we will see different control panels. And one of the punch card devices, the Pilot Ace used punch card for data and programs into the machine, and punched punch cards to get data out of the machine, and that's one of the items. Now, this photograph has been very carefully set, because behind it, just up here, is a huge black curtain. And on the next shot, unfortunately, it's not from quite the same angle. We can actually see what's behind the black curtain. And what's behind it, which is this huge cabinet here, is the memory of the machine, the mercury delay lines. Mercury delay lines, to work at a constant speed, need to be kept at a constant temperature. So this is a huge temperature-controlled case, and the dial at the end there is almost certainly a thermostat. So they'd hidden all of this from the press. A quick aside of the mercury delay lines, just to give some people that don't know. Imagine a thin tube about 1 inch in diameter, some 6 foot long generally, but perhaps folded, with transducers at either end. And if we apply a signal to one end of the transducer, as a ping, it would travel relatively slowly down the tube and be detected at the other end. Now, it takes only 1,000th of a second to get down to the other end, which is obviously it's pretty rapid if you're for us. But as far as the computer is concerned, it's slow enough that we can actually store almost 1,000 such pulses in the tube. Now, these must be experimental tubes because they're outside of the cabinet. In front of the machine, there are actually some of the shorter tubes, which are only some 10, 12 inches long. If we get a closer view, where are we? This is the operator desk now in 1953, which has changed quite significantly. The memory cabinet's still behind it, and the valve racks are disappearing out of shot there. We've got both bits of the card equipment there, Hollerith card machines, a card punch and a card reader. Simon's covered some of this already, but as Simon said, the actual design, which is a fantastic document, was presented to the NPL board in '46. And Turing effectively had gone by summer '47. But as we've said, construction actually began. Construction complete when the first machine was run was May 1950, and then a public demonstration at the end of the year. And then obviously the machine then went into service at NPL up until '56. A little bit about the machine itself. It's very, very fraught comparing machines, especially of that generation. It has a 1 megahertz clock cycle. Addition was anything between 64 and 1024 microseconds, and that potential spread is important, we'll come on to, but executed typically about 5,000 instructions per second. Trying to compare that with other machines at the time is difficult, but generally on a simple addition, it was some 15 to 20 times faster than, for instance, the Baby or EDSAC. But in terms of multiplication, it was similar. So depending on what the job was, it was potentially faster. The storage, the amount of memory the machine has got. Each of the words that the machine uses, the word size is 32 bits. It's provided with 8 of those long delay lines, each of which contains 32 words spinning around in those tubes, and 8 short delay lines, which were generally used for registers. The storage itself was actually increased, more memory tubes were added later on, and actually a drum was added later on as well. The peripherals were an 80-column card reader, an 80-column card punch, which is quite different from a lot of the other contemporary machines which used punch tape. Punch tape equipment was very well known, Creed was making a lot of it, it was generally available. But obviously NPL had a quite extensive set of equipment, holograph equipment that they were using for computation at the time. Now, this is probably a lesson for all of us. The actual public demonstrations that would take place, the 3 programs were demonstrated. The first was to calculate a day of the week given an arbitrary date. One of the people that actually that was at the public launch was the Duke of Edinburgh. So the Duke of Edinburgh's date of birth was entered onto the machine, the program was run, and the day of the week the Duke was born was displayed. Now, the data was entered in binary, the result came out in binary. For reasons we'll see later on, the binary was actually presented backwards compared with other machines. So whether it actually worked or not, it doesn't really matter, I think. The audience applauded and got away with it. Same with the highest common factor routine as well. The final routine, very, very technical, to do with tracing of potential paths of X-rays through complicated optics and lenses. That machine, that program was run and apparently finished. Everybody applauded. There was absolutely no idea by anybody whether it had actually worked or not at all. That wasn't the point. So the trick is to have something sufficiently complicated that no one can tell whether it worked. As long as the machine stops at the end and perhaps produces some output, you'll probably get away with it. Right, now, programming the pilot ace. This is the point at which Bill was saying you should be taking notes and we'll be asking questions later. I'm helped slightly by a quote from Turing saying that the actual process of constructing instruction tables or programs should be fascinating. So if the rest of my presentation isn't, it's my fault and not Turing's fault. Modern machines, typical machines, modern machines, machines of that generation were programmed in a very similar way. A typical instruction set would have a set of commands. You could store into memory locations, load from memory locations, multiply, subtract, divide. It was very consistent. If you could, in this example, we're loading the accumulator from memory address 25. And that is reasonable. Everybody understood if you could load from accumulator 25, you could probably store and add that same value back into that instruction. This is PDP 8 code, by the way. Given that instruction, and given the simple format and the regular format, it's very easy for programmers at the time to simply assemble that code in their head. And to write a very simple program, instructions follow in sequence: load A, a skip instruction, a jump instruction, a halt instruction. Programs follow step by step in sequence and only divert out of that sequence when we're doing a jump or a skip. And that was common for similar machines, but not for Pilot Ace, and is still basically the same format that most processors work in. Things like 8080 whatevers have a lot more registers, of course, But generally, programs follow in sequence. And we know that we can store and add to memory locations, and the operand, the instructions that are available for us, are well known. Not all machines have multiply, they'll all have add and potentially subtract. And we can work out from this is a 12-bit word, exactly how that instruction was put together. We look at the Pilot Ace. The Pilot Ace has got this huge 32-bit word at the top. Now we can pick out certain elements of this, and effectively these slides follow my gradual understanding of how the machine worked. We can pick out a source address. Okay, so we can get some data from a particular address, and we can pick out a destination address as well. So it seems likely that we can actually read data from one location and to store it to another location. There's a value that we can change the number of words that we can actually transfer, but in general it seems that there are a few extra bits there, but we can imagine that we can read data from one value and store it in another part of the store. What there isn't in any of that is an indication of what we can do. There's no add, there's no multiply, there's no divide, or logical instructions, or skip, or jump at all. We can just move from values from one location to another location. Well, let's carry on. At least we know that much about the machine. Given our new understanding of how this word fits together, we can pop in certain values. So let's have a source address of 15 and a target address of 16. Now our understanding is that that will transfer one word from the delay line 15 into delay line 16. And indeed it does. And that's exactly what that instruction will do. So whatever's in that one value gets copied, replaces the other location. It seems reasonable, because we're used to the fact that things work in all different directions. We could also then say, well, let's use the source of 15 and copy it into location 17. It's only one step further on. That seems to be a logical thing to do. It doesn't. It doesn't at all. Several of you in the audience are completely ahead of me here, who obviously know all about the ace. What it actually does is adds to the value in 16. And this, in my notes, is called spooky action all through the notes I've created. Because, in fact, actually, this destination 17 isn't actually a location at all. It's almost like a fake address. It's a route through the adder to add in to another value. The instruction set for the ace is full of these spooky action addresses, for want of a better name, that are apparently addresses, or source addresses or destination addresses, which actually have other functions. They can be used to initiate multiplication, they can subtract, they can also form jumps and skips as well. So in fact, the programmer's reference card, a programmer's reference card these days for machines, and certainly in the 50s and 60s, would list all of the instructions that were available, the stores, the loads, and the multiplies. The programmer's reference card for Pilot Ace simply listed what all these various hidden stores and this spooky action did, which were the locations that we used to add into the accumulator, which ones formed a jump. So we know a little bit now about the machine. What I have said, though, so far, is we can copy this source address, and the target address is a delay line. Well, we've already said that the delay line has a lot of words circulating through this delay line. We don't want to copy, if we want a value out of one of the delay lines, to copy it or to add it to another value, we don't want every word out of the delay line. But these words are spinning round, each 32-bit word whizzing around every thousandth of a second. Now, there are two extra bits of the instruction set here called wait and timing, which allow us to actually put in effectively delays, these are so-called, these lowest increments of the machine, minor cycles, to predict when the particular value that we're interested in is going to pop out the end of that delay line the next time. So we're obliged to actually be very close to the memory and understand exactly how the memory is doing. how the memory is working. So when we execute one instruction, we know that that instruction will take some time. We know the next value is, let's say, down here in the store, and it's going to be several cycles before that appears at the end of the store and is useful for us. So we need to put those delays in the instructions. Now that starts making things incredibly complicated. The other bits that we've ignored, the very first part of the instruction actually has an address of the next instruction. Now, when we looked at other machines before, the instructions follow on one to the next in strict sequence unless we jump out. Not the ACE. The ACE has an actual location of where the next instruction is coming from. Because in the same way, once you're actually executing one instruction, you don't want to wait around. You want to actually get on to the next instruction as quickly as possible. Well, you can predict and specify where the next instruction is coming from based on the instructions actually circulating in the delay lines. Now, Turing made a huge amount of use of this, as it's called optimum programming, to actually get every last drop of speed out of the machine. If the instruction set wasn't complicated enough to finish off most programmers, I suspect when you got to the timing in optimum programming, that really just was the straw that broke the camel's back. There are other delay line machines, of course, in use. The EDSAC machine used delay lines as well. But Maurice Wilkes famously said that he'd set his face against optimum programming, thought it was a distraction, because in fact he regarded the delay lines as really temporary and a better solution would come along. And there was no real point in actually getting bogged down in that. But Turing obviously made a huge amount of use of it. The sort of programming system that they used involved obviously flow charting and then gradually annotating these flow charts with the timing details that they needed. And gradually the program would be built that way from the flow chart. Eventually they were actually punched onto 80-column card. Helpfully, the card is actually overprinted with these details of the instruction word. So anyone looking at the cards actually can read what the instructions are. Now, before we get to the ACE itself, the ACE emulator, this is a picture that you've seen already. This is the Pilot ACE at the Science Museum. I'd like to zoom in on that control panel. I won't go through all of this, but that's the control panel as it obviously the final control panel from about 54 onwards on the machine. What we are doing at the museum is building a software version of that control panel, using a published emulator for the Pilot ACE and a big touchscreen built in the appropriate desk. So we need a software version of that panel, and if I click over, nothing happens. That's the software version of the control panel. Now I'll go through some of the things just what on the control panel now, and then we'll actually use the machine. Thankfully, we don't need to worry about holorith punches and card readers. So we have up in the spare section of the panel here to control for the card punch and a control for the card reader, which I'll be using shortly. There's a CRT display on the left-hand side, which it's not absolutely clear what that was used for in Pilot ACE, but we're assuming that the commercial machine Deuce used the display in exactly the same way. And I can select which of the delay line tubes I'm going to look at. Where are we? Over here, again, the instruction set, next instruction, the source, the destination, so on that we were looking at earlier, that I can use to set up instructions directly on the machine. We could actually enter the program I'm about to demonstrate step by step by step, and we could be here all night. Very useful debugging facilities that I can actually set a request stop. I can actually stop the machine on particular addresses. Now, I've read several places this was frowned upon, One did not sit at the machine slowly single-stepping and debugging programs when there's a queue of people behind you. There are a few nods from the audience there. But those facilities are there. There's a one-shot key over here and a number of one-shots I can provide on the telephone dial here. So I can actually single-step through code. I think it's a bit in for a dig, I think. It was not regarded. Down here, which we're not going to look at particularly, are the controls for the drum that was added later on. We talked about it being a 32-bit word, and we've got all these 32 bits across the bottom. Again, as I said earlier, contrary to pretty well, I think I'd say everything else in the world, the binary is displayed backwards. So the least significant bits on the left-hand side and the most significant bits on the right-hand side. It's not how we would write binary, and it's not how it's generally displayed. So we need to bear that in mind. So whenever we're reading values from the screen, it's backwards. It's known by, almost certainly not by Turing, but by Turing's colleagues as Chinese binary. Right, let me go back one. I need to swap and sit down over there for the moment. I think I've explained how complicated the machine was. I'd rather set myself up now for a fall by demonstrating the machine being used. Let's sit down. So I need to switch over to... Oh. Right. Again, this is the machine actually running. What I want to do is... first of all, I want to monitor. These are the tubes the switches I was talking about. I can change these switches. There's a mouse switch. I can change which memory store I'm actually. I'm just over there. I can look in the basic register that we're using in this particular program, or I can look in the delay line number 1. Now, the program we want to demonstrate is the program that officially known as successive digits, but was generally known as sucdigs. And it was a very early program that was used to test the machine and almost became the de facto test program on the machine. If you could load and run sucdigs, it was a good bet that the machine was actually up and running. A few people are a bit dubious in the audience here, but I think it was a good start. So the machine's idle at the moment, none of the lights are moving. What I want to do is load the program in. Now, typically what would happen is a deck of cards would be taken to the Hollerith card reader, dropped into the card reader, and the first card loaded. Well, I'm very luckily, and I think Turing would have loved this, I can simply go and say, load a set of cards. I've got quite a few cards there. The one I'm interested in is at the bottom, sucdigs, open. That's loaded the set of cards into the card reader. And across the top there, card position 1, I've got a neon that's lit. I've got a program ready to run. Now, we're looking at the delay line 1, where this program's going to go at the moment. So then I need to start the machine off on initial input over the top right and load that set of cards into memory. And that was a bit quick. I'll do that again. If we keep an eye on this side, I'll load the cards again. I'm getting on slow. No, right, move on. Oh, hang on. Sucdigs, load. Now, I'm going to click over here, the initial, but if you keep an eye on the actual delay line, we'll load that program into memory. So we're looking at that delay line now. We've got the program into memory. I'm going to start the program off over here with the, actually what I'm going to do is set, where are we? Let's clear that. There we are. I want to set bit 21 down here. It's a timing count. Start the program off with the one-shot key. Right, I think we've gone for that. Oh, hang on, I've actually stopped. I'm going to have to wait for that to finish for a second. The program's actually running at the moment. It's displaying the instructions it's actually working through at the moment. I can go over to the right-hand side and actually look at the register that I'm counting. And I think you can just about see there that that's actually counting up in binary. I'm going to turn that off because it will slow the emulation down. When that's finished, I will show you just once more, and let's put that on, move that up. Right. Let's clear operations, single shot again to start the program running, and actually what we're doing is slowly lighting the all 32 bits running that particular program. The program itself isn't modifying itself, it's running over there in the delay line, isn't changing, but if I actually look at one of the registers over there, then we can actually see that register counting. Now, let me get back. I realise I'm running late. Oh. A couple of final thoughts. We've talked about Turing and electronics earlier. I think Turing may well have been frustrated by the work of electronic engineers here in Hounslow Park and perhaps at MPL as well. And there's a certain frustration in this comment that too much experience of electronic circuits to believe they will work as they stand. I think there's a certain amount of annoyance here that he wasn't able to actually accurately predict mathematically how the circuit would behave, and rather gave up on that. He does make the comment, this is not a superstitious belief in the cussedness of circuits. I think he just regarded them as cussed and just impossible, and it was something for the men in the coats, the white coats, to work on. And the final thought for us programmers, when Turing gave the presentation to NPL, he was questioned very detailedly over the problems of actually writing programs for the machine. His answer, that the controller, the programmer, would have to take all these possibilities into account so that the construction of programs might be somewhat finicky business. So those of us in the industry who can actually sort of concur with that, it is a tricky and a finicky business. Thank you.
Thank you very much, Simon and Alan. We've got a few minutes for some questions. Okay, if anyone would like to ask a question, as I say, if you can come to the front, it just means we can film you, and we've got a microphone for you. Would anybody like to go first? Surely. Please, thank you. If you want to come to the front, it's not to humiliate you at all, it's just then we can catch you. If you actually stand back there with the hand on back. Perfect.
I'd just like to ask if the complexity of the Pilot ACE code process was a significant factor in your view in the sort of the whole USA versus Great Britain thing. So, who made the first computer, when was it released, that timeline with the little differences between, which one came out when. Did this have a role to play in that?
I would say the complexity of the Pilot ACE design did not play a significant part in which machine was actually built and implemented first. No. I mean, in a sense, all the early computers were complex pieces of electronics. Some had complex programming as well. Perhaps the quickest to catch on in the industrial sense were the ones that were easiest to program.
Do we have another question? Yeah, please.
It's not so much a question as a comment on what's just been spoken about.
Would you like to introduce yourself?
I'm Frank Blake. I'm probably one of the few people alive now who used to program Pilot ACE.
Sorry, your name was?
Frank Blake.
Oh, right, I've been reading
MPL.
Yeah.
And I think Turing was quite right in emphasising that this idea of programming being very complex was necessary to get the speed. I think it was definitely a philosophy of Turing's that he wanted optimum programming to exercise the minds of the programmers.
As programmers tend to be a relatively idle lot if we're not careful. I think
Thank you for that.
I think that sort of thing is completely obvious to Turing, and I think from what we've heard, he would simply say, well, it's completely obvious, and how could it be ever done any otherwise, at all? Perhaps found it a bit tricky and a bit finicky to actually to manage. But I'm sure that's a representation of exactly his thinking.
Thank you very much for sharing that with us. Do we have time for one more question? Yes, there's a gentleman at the back. If I could prevail upon you to come to the front.
So my name's Andrew Herbert. I was head of Microsoft Research, and I'm now leading the EDSAC replica project. This is more an observation than a question. If you look inside the microcode of several of the later machines, you actually find something that looks very much like the ACE structure. The register transfer language, magic stores. In the case of the Cambridge CAP computer, and I think the EDSAC 2, there was a thing called a V-store, and each location you poked did a different thing. And so for the microprogrammer who programmed the instructions that mere mortals had to use, one lived in that world, and you thought about timing cycles. So even those people who spurn optimum programming for users often did it inside the engineering of their own machines.
Oh, that's really good, isn't it? Yes.
And I mean, Andrew, would you argue, sorry, that sort of say at ARM, the engineers today are in fact living in that Turing-inspired world of timing cycles?
Yes, you very much are. And if you look at the architecture of modern microprocessors with lots of things happening in parallel, very long instruction words, you're absolutely in that world, and you wouldn't let an ordinary programmer near it. It's far too complicated. I say that with all the arrogance of someone who himself was a microprogrammer.
A final question. There's a hand up at the back, and then we'll break for conversation.
Hi, John Lane from the Register. I'm not a programmer, and I don't know very much about any of this side of things, but I'd like to ask about Turing. I mean, what comes out from your presentations is what an individualist he was, he was radical thinker, he was thinking about fundamental problems and so forth. Was his thinking and the way he acted any different when he was a code breaker? Because the work here at Bletchley Park seemed to be very much a collaborative effort, a team effort. You had mathematicians, linguists, people working, receiving radios, the secretaries and everything doing the essential grunt work. Was there any difference in how he was and how he collaborated with people when he was a code breaker? Thank you.
I don't think so. I think my understanding is, although there were thousands, 5,000 or 6,000 people working here at Bletchley Park, and let's say 99.9% of those would be working together and working in teams and a strict business, almost mechanized process. I think there was space for quite a few Cambridge and Oxford dons who were treated as sufficiently brilliant and sufficiently valuable that could actually get on and not necessarily be team players.
Well, I think we must also ask ourselves, why was it that Turing was sort of semi-detached from Bletchley Park and then eventually finally detached from Bletchley Park, so that for the final year of the war he was working on a completely different project, namely speech encryption at Hounslow Park.
And with that question, we're going to leave it for this evening, but I suspect there'll be an opportunity to engage with Simon and Kevin in the bar, which is, I understand, opening now. Thank you so much for coming this evening, everyone. It's been fantastic to hear this. It's been a very stimulating couple of presentations. I'm going to go and have a go with the Pilot Days emulator and drive myself mad, I think, with it. I'd like to thank Andy Clark for hosting us, National Museum of Computing, Kevin, obviously, and Simon. Also, Stephen Fleming, who did much to pull the event together, and Bletchley for giving us access to the ballroom this evening. Thank you all for coming.